Tanya. For those online that don't know me, my name is Sean McGill. I'm a research physical scientist here at CHL. And today I'm going to be talking about some ongoing work that was between, as Tanya said, CIRP and CODS, looking at some optically derived currents. And in this iteration of it, we applied some machine learning to it to see what would happen to some of our currents. This was a big effort. So some of the other members on the team are Spicer Bach, Dylan Anderson, and Brittany Bruder up at the FRF. And then we also had Miley McCann, who is a DoD SMART student out of the University of Southern California on this effort. So as everyone I know in this room is aware of, as well as most of the people online, surface zone currents are crucial when it comes to sediment transport in the coastal environment. These currents are driven by wave energy and can be split between any alongshore currents, typically just referred to as longshore currents, and any cross-shore, specifically rip currents were what we were interested in with this work. All these currents have implications from a sediment management perspective. We're doing federal beach construction, as well as any hard engineered structures. So we have jetties, groins, piers. We're going to have rip currents in those areas that are going to impact the sediment. So these are some considerations that we have to make. But outside of the Corps umbrella, we do have some water quality concerns that can be involved with these currents. A lot of biomaterial that's being carried by these currents. And again, swimmer safety, while that might be a focus of NOAA, we do work on these beaches with these projects. So swimmer safety can be a concern when we look at the safety constraints around these projects. In the past, we've been using a lot of in-situ instrumentation traditionally, but in recent years, we've switched to some more remote sensing mediums for this. When we use the in-situ, we often leave questions about some spatial variability. And as we all know, it's very hard to have long-term in-situ instruments to collect data in the surface and just how much energy is involved with there, how often the equipment is lost or covered. So by using remote sensing, we were able to kind of avoid those issues. So as I said, this is an optical currents focused project, and we use optical flow to be able to get these currents. So for those that are unfamiliar with optical flow, we're looking at the apparent motion between images. So for example, in the top right, if you have 5 images and we have a red dot that's moving between them, when we use these optical flow algorithms, we're going to be able to detect that movement. Because this is based specifically, the most important one is that brightness intensity is consistent between the images, but we can have variation between spatial and temporal with the images. Optical flow algorithms can be split up into 2 categories. So the first one is sparse algorithms. These are typically faster but coarse algorithms. You can manually select points of interest or run an algorithm to find points of interest, and it'll track between those images. So if I have an image holding, I'm holding this book right here, we can run a corner detection algorithm and it'll find the 4 corners of this book. And then the next image, we see that it's moved and we'll be able to connect those points there. We will have no idea what's going on with my hands. I could be waving up here. That's not going to be detected because we're focused on just this book. Dense algorithms are going to consider all those pixels. So in that same example, you would detect the movement of my hands. Because we are working with all the pixels, this is a much slower process. However, you are going to develop a finer resolution with this. And this was the type of algorithm that we used for this work, specifically the far and back method. As Tony mentioned, this has been an ongoing project and it's built up on some previous CIRP and CODS funded efforts. The biggest one was between Dylan and Spicer working on trying to find a novel method for measuring currents, specifically using the foam in the nearshore environment. So the first thing that they did was they created wave average movies, or WAMs, and they took the imagery, they did a moving average based on twice of the wave period, and then from there, they were able to track the foam between the images. They then took the drifters Specifically, we had high areas near the shoreline as well as offshore the breakpoint. So we're looking at pixel brightness, if you think back to that previous slide. So if you're not having foam in the offshore, which is not very common because we don't have the waves to break and generate it, you can't detect that movement out there. Also, once we're in the inshore, if you're having consistently waves breaking, you're going to have the highest intensity from those waves breaking. It's going to kind of shelter or hide out any of the other movements, and we're going to have more of an onshore bias to the current. And the key point to remember, as I said, foam is essential for this. Because we are working in the ocean environment, we want that brightness contrast to be able to detect this movement. So if there's no foam, it's really difficult to be able to find this movement between the images. So building on to that some more, so the Catalan method was developed in 2008 based off of some imagery and marine radar at the FRF. So what they did was they took the imagery and the radar and they synchronized them and looked at the same spatial and temporal ranges, and they were trying to make some comparisons between what was seen in the optical signal versus the radar scatter. So the radar is able to see the wave crests and the waves breaking, whereas the imagery was able to see the breaking waves in the relic foam. So because we have that shared overlap between the breaking wave of those two mediums, we're able to find that specific point of interest. And then whatever the optical sees that wasn't the breaking wave would be the relic foam, and whatever the radar sees that wasn't the breaking wave, that's the wave crest that's steepening. So this had a lot of good results. This was a bit of a manual method. You had to tinker with some of the parameters to it, but it did have good results, being able to designate those active breaking waves, any remnant foam, and the actual steepening of the wave. So Francisco Saez and his group went ahead and built on those methods and incorporated it into a machine learning algorithm. So it's the same methods from before, where we want to take imagery and radar to help train this convolutional neural network, or CNN, and we want to be able to identify the breaking waves from it. So they use a different data set. So this was some data collected at the FRF in the September of 2010. They used the radar and the imagery to find where our breaking waves were and trained the algorithm on that. So the algorithm works in a 512 by 512 area of interest. It has a moving window that kind of identifies where the waves would be. So that with the groundwork kind of laid, we had the conceptual idea for this experiment. So we knew that with the current methods, our running average was causing some aliasing in those wave conditions with the wide spectral spread. As I said, the current methods for our WAMs are twice the dominant wave period. So it is possible that we'll be missing anything that is slower than that wave period. We're talking from a rip current perspective, specifically transient or flash rip currents. Those can be on the order of 5 to 10 seconds sometimes, but if we're working with a 10 or 12 second period wave, we're averaging up to 20 to 24 seconds. So we're not going to capture that rip current right there. And additionally, as I said, the previous methods that Dylan and Spicer explored has the potential for some onshore bias because we are capturing those breaking waves because they are very clear in the imagery, and it's going to override any other movement in that area. So we have an onshore bias of the velocities. So why go optical currents? As I hinted on previously, it's really difficult for in situ instruments to be maintained for long periods of time. We're going to lose them, it's hard to deploy, and they're also expensive. When we're doing, taking these results to hand them off to be modeled better, we can't just have one instrument out there. So if one survives, it's kind of hard to model off of. Or if you think back to where we're doing this dense optical flow algorithm, we're going to be looking at each of these pixels in the domain. So we're going to have a lot more data points to pull from, and we're going to have a better chance of collecting all data from a spatial domain. So we're not going to have to worry about, was this object in the wrong location? Did it not exist? Did we not capture it? We're going to have a good spatial resolution right here with this. So that led us to our hypothesis. So, based off some of our previous work, said, hey, if we can identify these breaking waves using some of these existing methods, we're able to remove the bores before we create these WAMs, we're going to be left with just a residual foam, and that'll give us a more accurate surface current flow right there, because we're not having that onshore bias that's being created from breaking waves. So, experiment, we implemented this at DUNEX. So for those that are unfamiliar, DUNEX, which is short for the During Nearshore Event Experiment, was funded by the U.S. Coastal Research Program. It was a multi-agency, so multiple federal agencies, multiple universities, different stakeholders, all collaborating and coming to one place at one time with different experiments to complement each other. Because the idea was if we have all these experiments going on at the same time, collecting different data, we're going to be able to have a better picture of what's going on in the nearshore environment during these extreme coastal events. So this occurred with a pilot study in fall of 2019. Couldn't do it during 2020, self-explanatory, and then it picked up in fall of 2021 through the winter of 2022. So the methods of this specific part of DUNEX was processing the Argus imagery, and from that we wanted to generate our WAMs, or wave average movies. Once those were generated, we wanted to apply the machine learning to the raw imagery. So we're not applying it to the WAMs, we're just applying it to the raw imagery. From there, we wanted to go QA and QC all of our results. Where did the mask work? Was it good quality, okay quality, or bad quality? Once we found the ones where they were good quality and we could work with them, we then wanted to go ahead and run the optical flow algorithm on both the unmasked and the masked imagery. So we can make a comparison on what the optical currents look like and how some of this filtering can better change our results and remove that bias. And then, of course, compare that detected flow right there. So for those that are unfamiliar, the Argus Tower that we use is located at the FRF at Duck, North Carolina. The tower is 43 meters tall and has 6 cameras stationed on it. Traditionally, the images are captured at 2 hertz for 17 minutes at the top of the hour. However, for this experiment, we upped it to every 30 minutes, but the frequency was at just 1 hertz. Once the imagery has been collected, it was rectified and meshed to give a 1 by 1 meter resolution to give you that product at the bottom. So this is just 6 snapshots up top and then meshed and rectified at the bottom. And then that's done for 17 minutes to create a video of the near shore at the FRF. So then we need to apply the machine learning. So I have 3 videos playing right here. On the left is our raw Argus video. In the middle is what the machine learning is saying. So wherever it's black, that's not a breaking wave. Wherever it's white, that's saying, hey, there's a breaking wave right here. And on the third side, we've gone ahead and I've overlaid it. So anything that is a solid black is what's identified as a breaking wave. Now, you might be looking at that and saying, some of the residual foam is being collected. That is correct. That was the biggest cause of error when looking at this, was they would often detect sometimes residual foam behind the breaking wave. Billboard going into Erdic and say, hey, here's our machine learning product right here. It works. Neutral quality, I consider that, we might have some instances in this, we're capturing some of the foam behind, but there is some workable components of it. And then our bad quality maps were any times where it was just predominantly foam detection and instances where there were breaking waves, but they weren't detected, or if we had clouds going overhead, because that changes in brightness, we would oftentimes have gaps in the wave detection. So, results. This is where we're at right now. There's 80 terabytes of DUNEX data that needs to be processed. Every time we try to process it, because it's such a large data set, RDE clamps down and triggers a shutdown of the communications at the switch. It says, nope, can't do that. So currently working to figure out why this is happening and what can be done to rectify, because we got a decent chunk of data still to go through. We're pushing through, making work of it, but it is fairly slow in the meantime. But for this discussion, we're going to take a look at the 133 videos that were manually reviewed for the mass quality and kind process. So of our 133, we had 3 that I considered to be good quality, which is not a lot. However, 49 of those, we had a decent, showing. We could be able to see some wave rollers captured. It might have been some residual foam, but enough where you could work with it. And then 81 of those were bad quality. So that gives us about a 60% failure rate or a 40% accuracy, which is kind of not what we were expecting. So we wanted to dive in a bit more and see what's going on. So I know there's a couple figures up here. I'm going to walk through each of these, starting with kind of general overview. So anything that is blue, that was a good or neutral quality mass. We could work with that. Red was bad. If it is a circle, that means that was a plunging breaker. And if it was an X, it was a spilling breaker. So starting with the top left, we were looking at, where was the sun's position in the sky when we were collecting this? So the sun's azimuth, if you think about that, that's degrees from, east to west. So where, how close is it from sunrise, high noon, sunset? Whereas the sun elevation, if you're looking at the horizon, is that angle between the horizon and where it is in the sky. So you can kind of see our good quality mass kind of stuck just in the early pre-noon hours. There was, a day or two where we did get some in the late afternoon, but for the most part it was in the morning. Whereas our bad quality mass were captured all parts of the day. Next to the right, we're looking at the wave period versus the wave height. There's not a trend there. We couldn't see anything. Maybe if we pull in some more data, maybe something might develop, but as of this instance, we couldn't see a trend. And the same thing with the bottom left when we're looking at our windrows. We couldn't find any trends there. But when we considered the ear bearing number, we did start to see another slight trend appear right there. So when we were categorizing them as spilling versus plunging, when we start the spilling, we have a high, we have lots of inaccurate mass. Whereas when we're in the plunging, we start to have better accuracy there. Specifically, when we're looking at the spilling waves, 31% of those were bad quality. Whereas if we were working with the plunging, we had about 56% good quality. So it was almost a little shot twice as accurate. Looking through some of the videos, we think part of that is because we're detecting, our false detections are due to the foam being detected. So if you have a plunging breaker, your residual foam is really confined to a small area. Whereas you have a spilling breaker, as it's going through the surf zone, you have a lot of the foam kind of falling behind it, giving it some detections that it's able to make. Again, we're just kind of hypothesizing off of this right now, but the sun's characteristics as well as the ear bearing was very interesting. So we want to look into it a little bit more. So here I've gone in and I've made the assumption that the sun's elevation and azimuth, because of our data collection was within 1 month, we're not looking at summer versus winter, I assumed it was the same at every time across days. So 11 o'clock at day 1 through 32, I assume that the sun is at the same point in the sky, just to streamline this a bit. And then I want to look at what was our frequency of what we considered, a good or neutral mask, a bad mask. What was the frequency of plunging versus spilling waves right there? And you can kind of see that the good and neutral are almost grouped with the plunging, as well as the bad and spilling are grouped together. So that leads us kind of to a follow-up, are we seeing good mass quality because it's occurring in the morning hours where we're having better brightness? Or was that because our plunging breakers during our capture period only occurred during the morning? So again, some more data will help us try and flesh this out to figure out, is it brightness? Is it the actual type of breaking wave? Or is it really a combination of the two? So that's something that we hope as we process this a bit more, some of these might kind of flesh out a bit more. But that's where we're at kind of from the mass quality and what's causing it. Let's look at some of the examples where we did have success of the mass. What did it do to our currents? So here we have on the left our raw WAM, and on the right we have our mass WAM. So when we're generating these WAMs, the raw follows its typical point of doing a moving average twice the wave period, whereas our mass, we would go image by image and apply the mass to it. So the mass was done at each image, it wasn't averaging. So when you see on the right side, any of these black blobs that kind of poke up in the break area, that is areas where the mass completely removed any waves. So you can see a bit of a darker foam because we are masking out some of those waves on that right. And we're seeing some more noise popping up specifically around those areas where we do mask out, because it does cause the algorithm to see that black around or black circle surrounded by white as an area to kind of follow. And again, red is going to be anything that is depicting movement to the north. Blue is depicting anything to the south. I know this looks like a lot. There's not a lot to pull out from it. So let's take a step back and let's look at from like a 5-minute average. So if we look at some stream plots for 5-minute averages, we can kind of see where we're having some of these currents going. So again, raw is on the left, mass is on the right. Some things that should be pointed out right here. So we see the onshore propagation on both sides. That's that red vectors right there. And the offshore movement is the blue. If we kind of hone in right in this area right here, where we did have a little bit of offshore flow, which is, a rip current in this situation, you're able to see the ejection of the energy right there at that rip head. When we went in and masked it, it was able to remove that onshore movement in the rip neck area, but we didn't get any offshore movement. That might be because there just wasn't any foam moving when we did the filtering again, because we do have that issue with some aliasing where we are removing some of these features to detect with this optical flow. So let's look at from, this is the 5-minute average right here. Let's look at that whole entire 17-minute collect real quick. So I know this is a lot again right here, so I'll kind of break it down. So up top is our 3 figures is the U component of our velocity, and then the bottom is our V component of the velocity. Any of the red on the top is going to be our onshore flow, blue is going to be our offshore. On the bottom, blue is going to be our southerly transport, and red is going to be our northerly transport. On that far right, we have our difference grid between the raw and the mass images right there. So if you see raw, you're seeing a decrease in velocity. Blue is an increase in velocity, regardless of what direction we're going. So the first thing that kind of pops out right there that we should see is we have this, we're capturing the head of the rib, ejecting out of the braking zone right there. And if we look just inside that on both the raw and the mass, you can see how bright on the raw that red is, whereas when we move over to the mass, it's a lot duller. That's because we are removing these wave rollers accurately. We are causing the detected velocities to be more offshore. We're removing that onshore bias right there. Another thing I want to point out, which you can see in this area, is this is a convergence zone. So again, even though we're not seeing that specific offshore movement in the rip neck, you are detecting those feeder currents leading into where we suspect the neck to be. Again, we might not be detecting that because of aliasing issues, we're not sampling it fast enough, or it could just be that there was no foam moving in that area at the time. I want to make that clear. Foam is very critical for these detections when we're working with this. So if we have a hydrodynamic rip that has no foam or sediment because it's just a slow velocity rip current, that might not be detected because there's just nothing for it to visually detect. So what were some of the implications to the transport rates? So for the U component, we had a 43% decrease in the velocity onshore. So we're removing that bias. That's huge, 43% velocity. In the longshore component, we had a 17% decrease. So it's good to see that we are having some success removing those onshore velocities that are caused not by the actual currents, but by the detection of the waves and falsely causing the optical currents to be faster than they appear. What about the Timex images? So again, this is a common data product when we're working with imagery in the coastal environment. So same thing as before, we have our raw Timex, what you would expect to see. In the middle, this is the Timex of the machine learning algorithm, so where the detection of the waves were. And on the far right, we have the mass version of it. So we've pulled out those areas where we're consistently having the break right there. So if you think about that far right one is more of a foam Timex now, whereas the one on the left is going to be both foam and breaking waves. Now, some of you guys might be seeing up in the top some of these straight lines that appear to be relics. And I kind of want to focus on that a little bit to wrap up the conversation, to highlight something that does warrant further investigation. So if we look at this image, we can see this very harsh kind of stop right here. It's a Timex, so there's some consistent wall there for whatever reason I want to call it. So let's go ahead, we pull out one of the instantaneous clips, and we do see that wall, almost like it's saying, hey, you can't detect anything past this part right here. This does cause some issues. Look into it more. I was like, okay, is it, something is just like breaking right there? But when I overlaid it on the actual imagery, we're not catching that from the wave roller. It is getting stopped. So this goes back to some of the flaws within the machine learning. As I said, it's got that moving window right there, and detects the threshold to be able to say, yeah, it's a wave that's breaking. For whatever reason, consistently in this area, it would stop right there and say, nope, there's nothing here. This is not one of our machine learning algorithms, so it will require some more work to kind of get under the hood and see exactly what's causing that. But that was just another interesting thing to kind of bring in mind when we're looking at that, is some of these issues are not so much the oceanographic conditions, but more of just flaws within the machine learning. So I know that's a lot, so kind of bring it back, wrap it up, and talk some of the next steps right here. So we applied the machine learning mask, and while we didn't have the most accurate mask that we expected it, we did have some success when we did have good mask quality. A bit of that onshore bias, which was an issue that was presented in Dylan's previous work. So I really want to stress that while machine learning did not work to the standard that we were expecting, when it did work, it worked really well. It was removing these biases that were an issue previously, and it opens the door for some other routes we can go about. So we know that the machine learning might not be the way to go about, but Catalan's method of filtering with both the wave roller and the radar works remarkably well. There was radar at the DNX experiment. So that will probably be the next step, is to look at, how are we going to get better results with that, which is kind of what we expect. So it's still worth investigating, because it is very important to try and see if we can limit this bias right there. If we are able to, find this method that works really well, it's going to be important to incorporate that with some shorter temporal windows. So we're not capturing these transient rips I talked about earlier that might be on the order of 10 seconds, just because we're filtering that out. But if we're able to filter the waves with the machine learning algorithm, we might not have to do these WAMs that are twice the wave period. We might be able to do more of a instant, or maybe a 2 or 3 second moving window, because the only noise at that point will just be just static spatial noise that you get from any algorithm that's using optical flow, which can, again, be smoothed out. As I said, we did have a lower than expected mass accuracy. We're really hoping that as we process this more, we'll be able to really figure out, was it the breaking wave, was it the brightness in the image, or was it a combination of the two? For the next step perspective, we're going to continue processing the imagery, and we plan to host it on the ERDIC library once it is completed. There were drifters that were deployed during this, and Miley McCann is going to be looking at trying to validate those currents that were detected from the imagery with those in situ. And then, as I said, we'll probably try looking at the radar and see if we can get some better results with that. And then, as Tony and I were talking earlier, some people overheard, we're planning to do a small little tech note on this effort because it is important to at least highlight, hey, if you can filter out the waves, you're going to get better results. So we might, focus on when it worked, why it works. That way, if someone tries to replicate this down the line, they can either use the SIAS model or they can find out a way to filter the waves to really get those more refined velocities. So at that point, I'll go ahead and open it to questions.